starting with vector addition. We have an F1 and an F2, and we add them together to get the force resultant. With vector addition, you simply take the x component of each of them and add them together to find the resultant x component, and you add together the two y components to find the resultant y component.
So as you can see here, we have a force F2 and F1, and we're trying to find the resultant force. So when you have forces that are either in the negative x direction or in the negative y direction, we just have to subtract those. So as we talked about, we're going to break it down at F1x, F1y, F2x, F2y. Right here, since we have the F2 in the negative x direction, we're just going to subtract those two, but we're going to continue to add the y directions.
So our next topic is scalar multiplication of vectors. If we were to multiply the scalar a times the vector f1, you would simply multiply a by the x component and then a by the y component. For a numerical example, if we say f1 equals 6 and 3, and we multiply 5 by f1, we'll get 30 in the x direction and 15 in the y. Alright, so next we're talking about vector decomposition. So if you're given just a force and not the components, you'll use the relationship f1x equals f1 times cosine of the angle of the vector, and then f1y equals f1 sine angle of the vector. And then once we have our components, we can put it in the proper vector form of f equals f1xi, which denotes it's in the x direction, plus f1yj, which denotes it's in the y direction. So just for a quick numerical example, we'll say f1 equals 5 and alpha equals 45. f1x will equal 5 times cosine of 45, and f1y will equal 5 sine of 45, which will give us values of 3.5-ish and 3.5. So then we can put it in our final vector notation. Say 3.5i plus 3.5j.
So we talked about vector decomposition, and now it's time to do an example. So we have everything worked out for you, but we're going to walk you through it. So right here we have forces F1, F2, and F3, and we need to decompose them into our x and y components. So what we're going to first do is decompose F1. That's our easiest since it's along our x-axis. So we have 300 newtons along our x-axis and 0 newtons along our y-axis. So the vector form is 300i plus 0j newtons. Next one we're going to decompose is force 2, which is 400 newtons. And using our relationships, we know that F2x is going to be 400 newtons times cosine 30, which gives us 346.4 newtons. In our y direction, it's going to be 400 newtons times sine 30, which is going to give us 200 newtons in our y direction. Now for F3, we really don't have an angle, but we can use a similar triangle relationship. And we're going to do, for the x direction, 250 newtons times 4 over 5. That's going to give us 200 newtons. And then our y direction, we're going to do 250 times 3 over 5, which is going to give us 150. So over here, we've just written our F2 and our F3 in our vector form. So it's going to be 346.4i plus 200j newtons. Now F3, if we notice, our x is actually negative x. So we have to remember that. Our F3 vector is now going to be negative 200i plus 150j newtons. So to find a resultant force, all we do is either add or subtract all of these up. So right here it's going to be 300 plus 346.4 minus 200i plus 0 plus 200 plus 150j newtons. When we do this math, we find that our resultant force is 446.4i plus 350j newtons. And if we wanted to find the magnitude, we know we just take the square root of both of these values squared. So when we do that, we find the magnitude is 567.2 newtons. And the last thing we need to do is we need to find the angle relative to the x-axis that our resultant force is going off of. So here we use this formula. Theta of the resultant force is the inverse of tangent of the y direction of the resultant over the x direction of the resultant. So here we have it plugged in, and we get an angle of about 38.1 degrees.